Okay, so we looked at the Green's function for the wave equation last time around, with a little slip up of something that I thought I'd done previously, but I did not. But we rectified that, looked at the initial problem for initial value problem for ODEs, and we saw that by looking at Fourier transformations of just the x variable, we could turn the solution. Turn the problem of the Green's function of the wave equation back to something that we know, and we solved it. And yeah, so that's what we did last time around. And this time, what we will do is we will look at Poisson's equation. Okay, so we will look at Poisson's equation, and we'll try and solve that. That we'll try and get the Green's function, and that's what we're going to do. All right, so let's start. Share the screen. And remember to turn myself off. Yeah, so Poisson equation. So a Poisson equation for a function phi goes from Rn to C is the forced Laplace equation. So this is the forced Laplace equation. So this is del squared phi equal to minus f of x. Now this minus sign is just a matter of choice. It's it's a convention at the end of the day. So we want to construct the Green's function, and this is going to be a little less straightforward than what we did before, and Fourier transforms will not be used. Okay. Now the fundamental solution. So fundamental solution to the, let's call this G of n, to the Poisson equation in n dimensions is defined to be the solution of the problem del squared Gn xy n x minus y. Okay. Where you choose your forcing term it to be this n-dimensional delta function. Since the problem is rotationally symmetric about the point y, this special point y, the fundamental domain can only depend on the scalar distance from that point. So Gn xy is equal to Gn of the modulus of x minus y. Okay. Now you can take this equation above and you can integrate both sides over, say, a ball. So let's integrate over a ball BR, which is x is an Rn such that x minus y is less than or equal to R. So this is centered around y. And what we obtain is simply, 1 is equal to integral of dpr dgn dr. Oh, sorry. Yes, we will get to that, but not yet. So del squared gn dv, which is equivalent to, using the divergence theorem, this is going to be equal to del br n dot del gn ds, where del br now is the boundary of the boundary sphere. So this is x belonging to Rn such that mod of x minus y is equal to R. Okay. For n equal to 2, this is just a tangent sphere. For n equal to 3, so for n equal to 3, this is just this standard sphere. For n equal to 2, this is a circle. If you have n greater than 3, then this is a hypersphere, and so on and so forth. Now, in each case, the outward pointing normal n points in the radial direction. So this guy that you get, this thing, is just equal to, this is just equal to dgn dr. Okay, so hence what we obtain is that 1 is equal to integral del br dgn dr r to the n minus 1 d omega n, which is r to the n minus 1 dgn dr integral of s n minus 1 of d omega n. Okay, so yeah. So over here, so we have this integral over the sphere, and d omega is simple. For example, if you are looking at d equal to 3, then d omega is sine theta d theta d phi. And if you're looking for d omega n equal to 2, that's just d theta, and so on and so forth. So you can do this integral. So what you get is so if you have so what you get is dg n dr. This is 1 over area r to the n minus 1. So a, let's call this an. So a, for example, a3 is equal to 4 pi, a2 is equal to 2 pi, and so on. This is again everything that you guys know. So g is then simply modulus of x minus y plus some c1. If n is equal to 1, 1 over 2 pi log of x minus y plus c2 for n equal to 2, and minus 1 over a n to the n minus 2, 1 by modulus of x minus y to the n minus 2 plus some c3. So all of these, this one is for n greater than equal to 3. Okay. So for n greater than equal to 3, we can actually see, no, let's not call this C3, let's call this Cn actually. For n greater than equal to 3, we can fix Cn by requiring, say, limit of x goes to infinity, or sorry, not x, limit of r goes to infinity, g of r is equal to 0. This cannot, however, be imposed in 1 or 2 dimensions, and you need to put in some other sort of boundary condition suggested by the details of a particular problem. Okay. Now, when n is greater than 1, the fundamental solutions obey the Laplace equation for all of these things. When for all x, when x is not equal to y, but they become singular at x equal to y. So what we have to do now is we have to exercise special care when you using them as Green's functions for the Poisson equation throughout Rn. Okay, so let's do that. Let's try to understand that a bit. So this is where we want to focus on things called Green's identities. So the Green's identities are identities that establish relations between the fundamental solutions Gn and the solutions of the Poisson equation. Okay. Now we are going to start off by supposing that we have, omega, which is a subset. Sorry, omega, which is a subset of Rn. This is a compact set with boundary d omega. Now, we let phi and psi be two functions on omega that are regular throughout omega. Okay. So the integral, so the product rule and the divergence theorem is going to give us the following. So if you have omega of grad of this is going to be simply psi del squared phi minus, so phi psi dv. Okay, so this is now, as we said, this first the product rule, and okay, sorry, what am I doing? I have interchanged a few things. Let me just so that was phi del squared psi plus, yeah, and this is nothing but del omega of phi and del psi dx. Okay. So that is going to be Yeah, so n here is the outward pointing normal to del, del omega. And so yeah, so that's this. So this particular identity is going to be called Green's first identity. And now let's interchange psi and phi. So then what you have is del of psi phi dv is going to be similarly psi to n dot phi ds, right? So if we subtract the two, then what we are going to get is that the over, omega phi del squared psi minus psi del squared phi, this is going to be given by integral del omega of, so this was again del of these two terms now, right? So this is phi n dot grad psi minus psi n dot grad phi, this into ds. Okay. The second equation, this equation in blue, is Green's second identity. So in order to make use of these results, we would like to apply this to the case where psi is g of n, our fundamental solution. Okay. However, g of n is singular at x equal to y. So it's not clear how the thing that we have done so far is actually valid, because the divergence theorem, for one, requires requires the functions to be actually regular throughout throughout omega, and so one has to be a little more careful than this. So now let's reattempt this. Okay. So now let's take a ball b epsilon, and this b epsilon is going to be a ball of radius epsilon, which is much less than 1, and this is going to be centered around this, centered around y. Okay, centered around y. So this is a ball centered around this dangerous point y, and omega, let us say, is actually b of r, the thing that we were looking at before, minus b of epsilon. So we excluded this point. Okay. So x belongs to Rn such that epsilon is less than equal to modulus of x minus y is less than equal to R. Okay, so that's what it is. Now Gn is particularly, is perfectly fine in this, in this particular region. So we can apply Green's second theorem now here. And let's do that. So if we do that, we do the following. So this is over omega phi del squared Gn minus Gn del squared phi on dv is equal to integral of minus Gn del squared phi dv. This is still on omega. This happens because, remember that del squared gn is equal to 0. And yeah. So here, so this is equal to integral of del of omega phi n dot grad of, oh, sorry, minus gn of n dot del phi ds. So we have just applied Green's identity here. Now we are going to split this up into the thing that, so there are two boundaries. Now one is at SR and one is at epsilon. So let's split this up. So there's an integral of on SR, so Sn minus 1R, the same guy here, plus another contribution from S epsilon n minus 1. So this, curly brackets just means the stuff that is here, that is both here and here, okay? Now, for the inner boundary, the sphere of radius, epsilon, the outward pointing unit normal is actually minus of r cap, okay? So what is going to happen? So inner boundary n cap is equal to minus r cap. So Gn of the inner boundary is going to have these signs to it. So there's minus 1 over an minus 2, 1 over epsilon to the n minus 2. And if you find out what n cap grad Gn of the inner boundary is, then this simply turns out to be 1 over an 1 over epsilon to the minus 1. If you are thinking about a measure of the n plus 1 dimensional sphere of radius epsilon, so ds is nothing but epsilon to the n minus 1 d omega n. And again, d omega n is an integral over angles. So what you have is, when you do this, s epsilon n minus 1, so minus gn so what you get, so what you want is this guy here now. So this final term in this last equality is the following. So this is just given by Gn n dot grad of phi ds is epsilon times integral of n dot phi d omega. Okay, so that's that. And that was one of the terms, of course. So that was one of the terms. So you have, so you know, so this what we were doing is that there is, okay, so there is this thing. So there is I mean a term like this and a so a term like this and a term like this. So this term we have, I mean, evaluated for S epsilon. Now we need to evaluate this term for S epsilon. So let's do that now. So since y is regular at, I mean, sorry, phi is regular at y by assumption, and the value of the remaining integral is bounded, we can look at this. Yeah. So okay. So let's just yeah, evaluate the last term. Let's just get to the last term then. So yeah. So S epsilon n minus 1 phi of n dot del gn ds. So this is going to be minus 1 over an integral of phi t omega n. This is by the stuff that we did here, and this simply is given by minus phi, let's call this phi bar, which is the average. Okay, so this is essentially just the average. That is what we do. And so now, so what we get at the end of the day are these two guys, which give you the what is happening at S epsilon. Now notice that you have something here which is multiplied by an epsilon in front. Since phi is regular by assumption at y, so the value of this integral that you have is going to be bounded. So this is multiplied by something, epsilon, and this is this is a finite thing at the end of the day. So when you get epsilon going to 0, when you take epsilon going to 0, this whole term actually goes away. On the other hand, this one does not. When you shrink the sphere to a 0 size, what is going to happen is that you're going to replace this phi bar by just phi. Okay, this is just going to be replaced by minus phi of y when you are going to the limit of epsilon going to 0. So what we get is we put all of this, back together. Then we get the following. We get phi of y is equal to integral over omega gn del squared phi dv plus integral over del omega phi n dot del gn skip minus gn, sorry, running out of space. Let's move this here. Let's move this away a little bit here. Gn n dot bet phi ds. So this is what we have. So we just put all of this, all of this here. So now what we have done is that we have taken, this is our new form of Green's second identity involving Gn, where now we take the boundary of this, I mean, omega, this as is del omega, just to be the largest sphere, since we have shrunk the radius of the inner sphere, I mean, down to 0. Okay, so that's useful. Finally, what we will do is we are going to take del squared of v. So del squared of phi, sorry, is equal to minus f. So what happens is that we are going to obtain something which we call Green's third identity. So this is going to be phi of y is equal to integral gn of xy f of x dv, there's a minus sign, plus there is this piece from del omega now. So phi x n dot del g and xy minus g of xy, and I'm out of space again. N dot del phi x. This whole thing is ds. Integrals are over the x, I mean x variable. Okay. So this is indeed a remarkable formula. Just recall that y can be any point in Rn, and we see that this particular equation in red describes a solution throughout our domain in terms of solutions on the boundary, the known function Gn, and the forcing term. I mean, also it's important to note that the Green's function here is provided as an expression for the solutions with the solution with inhomogeneous boundary condition. Okay, so provided n and del phi tend to 0 suitably fast at asymptotically large distances, you can actually drop these boundary terms, and then you're just left with you're just left with the first term of it. In that case, Green's third identity shows that Gn is the free space Green's function for the Poisson equation. This also allows us to formally allows us to write down the following. So also, so what you can write down is the following: del squared of phi of y is equal to minus integral of Rn over Rn del squared Gn xy f of x dv. This is formally then just, so you can just do this. So So formally, this is Rn del n x minus y f of x dv. So this is just minus f of y. This is like you wanted just from the start. Okay. All right. So now there's something a little unnerving about this last equation that we wrote down. This equation in red. If you set f equal to 0, this provides an expression for the solution of the Laplace equation in the interior domain omega in terms of values of both n, both phi and n dot del phi on the boundary. But we already know that if, omega is a compact domain with a boundary del omega, then specifying phi on del omega alone is enough to give you a unique solution to Laplace's equation. This is just, usual Dirichlet boundary conditions. Or you can apply Neumann boundary conditions, which is just n dot del phi on this d omega. This also gives you a unique, unique solution. So how do we, how can we explain something here which has both n, both phi and n del phi? The point is, while this equation with f equal to 0 is a valid expression obeyed by any solution to Laplace's equation, it's not a constructive expression. That is, we cannot use it to solve phi in terms of boundary data, because phi and n dot del phi cannot be specified independently. Okay, this is something that one would like to keep in mind. Okay, so with that, I'm going to close this particular lecture, and we will have one last lecture where we are going to be looking at Dirichlet-Green's functions for the Laplace and Poisson equations, and finally a method of images to wrap up our course. Okay. All right then. I will see you soon again.